Okay, then hello everyone. Today we welcome Grégoire Mathys from Amsterdam, and he will talk about Einstein-gravity from ANEC correlators. So please.
Hello, thank you for inviting me to talk about this work that I did with Alex Berlin and Grégoire Mathys in Amsterdam. That is indeed called Einstein-gravity from ANEC correlators. So the plan of today is to start with the main question, to highlight the main ideas using 2D CFT that is a bit simpler, but many things go through to higher dimensions. Then we want to recast the ANEC as a differential operator and go through the scalar example. Then discuss how large N and large gap help us in doing what we want to do, and how this leads to A equals C. And then I'll finish with the conclusion and then the outlook. So if you believe in ADS CFT, and I think everybody does here, you can see every CFT as giving rise to a theory of quantum gravity in ADS. But typically the bulk dual will be highly curved in quantum, and it's not clear whether it will be useful or not. So the natural question that arises is what are the necessary and sufficient conditions that a CFT must satisfy in order to have a weakly coupled Einstein-gravity dual? This question was sort of initiated by this paper of Himskirk, Penedonius, Polchinski, Solly, where they conjectured that the large N and large higher spin gap is dual to weakly coupled local gravity. And I will come back to that in a minute. So if you want a recoupling in the bulk, this is actually a statement about 3-point function of the CFT stress tensor. So if you take this combination here, that is the normally, that is the well, that is appropriately, yeah, whatever, that scales appropriately under scaling. This goes like square root of Gn. And if you take the 2D case, then you have only one tensor structure in this 3-point function of TDT that goes like C. And so this combination here goes like C to the minus 1/2. So if you want a weakly coupled gravity, you have to have large C. So large number of degrees of freedom. Now in 4D, the story is a bit different. The 3-point function has 3 different tensor structures that are known, and you can look them up in this fairly old paper. And so here the 0, 2, and 4 label the spin when you decompose this under irreducible representations. And this tensor structure is dual to Einstein gravity. This will be dual to R2 term, and this will be dual to R3 term in the bulk Lagrangian. And you see that here you have an overall T0 that is the constant that multiplies the Einstein term. And if you want to have every quantum gravity theory flying to Einstein gravity in the IR, then you would expect A2 and alpha 2 and alpha 4 to be of order 1 in this dual bulk effective Lagrangian. And then a natural question that rises: can you bump those numbers up? Because you have an overall 1/Gn, then this will still be weakly coupled, even if these numbers are bigger than order 1. But if you do this, then you might violate the universality of Einstein gravity being the IR description of every well-behaved quantum gravity theory. And so it was shown by a study of microcausality in bulk high energy scattering processes that actually those alpha n have to be like delta gap to the minus n, where delta gap is the dimension of the lightest operator with spin greater than 2. So this is work by Camaño, Edelstein, Madison, Aziboidov. But if you take a theory with large gap, then alpha 1 and alpha 2, or alpha 2 and alpha 4, sorry, must effectively vanish. And if they vanish, then if alpha 2 and alpha 4 vanishes, then T2 and T4 have to vanish. And if T2 and T4 vanishes, then A has to be equal to C, because those T2 and T4 are just linear combination of OPE coefficients. So that's the way you would like to prove A has to be equal to C. Now, what we did in our work was using average null energy operators, which are just defined like this. So they're just the integral over a null line of t minus minus component of the stress energy tensor. And it has been shown that the expectation value of this operator is positive in any state in the Hilbert space, which is one of the nice properties that we will use afterwards. And if inserted at the same like coordinates, but in a different transverse position, they are space-like separated, and so you expect those operators to commute. So this is a bit subtle, but this was shown in full generality in this paper by Kologlu, Kravchuk, Simons, Duffin, and Ziboirov, exactly at the same day we published our paper. So I think now it's a settled issue. So in the end, what we will do is studying higher point function correlators of ANEC operators in large N and large gap theories. And we will show that both this implies A has to be equal to C in two different ways. One is to compute the correlator, the commutator, sorry, of two ANECs in a TT state, and this directly implies A has to be equal to C. And the second way is to compute the K point function or N point function in this case of ANEC operators in T states. And we will see that the more ANEC insertion you put here, the smaller the bounds on A minus C become. So this delta N is strictly decreasing, and I will show some plots later in the talk. So I would like to start with the two-dimensional warm-up because 2D CFTs are really easy and you have a lot of control over everything, but you have many ingredients that appear in 2D and that will just go through in 4D in a more complicated way, but still tractable. So the 2D ANEC is just the integral of T of Z. So you know in 2D you have T of Z and T of Z bar, and you just take a Z integral of this, and the free-point function or any endpoint function of the stress energy tensor is completely fixed by word identities, and you can just compute it. So you can just take the free-point function here that is fully fixed and integrate it. So do this integral, and you end up with a free-point function of two T's and an ANEC, and this is just given like this. So you need to be slightly careful about ordering, and you need to take I epsilon prescriptions and do this in the right way, but you can just do it straight away. But now you can also just open this, expand this T of Z as a Laurent series, right? And if you do this, then the only term that will matter is the 1 over Z term. So it's the L minus 1 in the Laurent series. And this is just, roughly speaking, a derivative with respect to Z. So you see that in 2D, the ANEC operator is just exactly a differential operator. And then if you want to compute a higher order correlation function with K insertion of the ANEC operators, and what you will have to do is just taking K derivatives of whatever remains in this. So in this case, it's going to be a 2-point function. And you just need to take the appropriate K derivatives here. So it looks a bit surprising because you need an infinite sum to reproduce the endpoint correlation function of local operators in 2D. But this ANEC looks like it's completely fixed by symmetry. And we'll see that this propagates to the 4D case. But so now you can also reproduce this in a different way, that is taking the OPE. I mean, it looks different, but it's actually the same thing. So the OPE of 2 T's is just given by this well-known formula. But now say you take the free-point function and you fuse Z2 and Z3 in an OPE. Then you have this term will give you a 1-point function of T of Z1 that just vanishes. And then you have this term gives you this contribution with a 2-point function, and this term gives you this contribution with a derivative of the 2-point function. And now you want to take the integral as z2 goes to z3, and you see that this is a second order pole, and this has no z2, z3 pole, so this just vanishes. And this one, what it does is removing this part when you take the integral, and giving you exactly this contribution, so this derivative times the 2-point function. And you see that this is exactly what we said before, that the ANEC was just a z derivative of the acting on the right thing. And you can do this. You take this, you integrate once by putting the actual form of the 2-point function, and you get back to the same result.
One question.
Yes?
Are you working in the vacuum here?
Yes.
Okay. Okay.
Yes.
Thanks.
And so now let's look at 4-point functions. So 4-point functions are also completely fixed by symmetry. You can just write it. You do the 2 integrals that you need to do. You take care of the I epsilons, and you end up with a finite result here. And you can do the same game that we played before. So you want to fuse Z1 and Z2 and Z3 and Z4 in an OPE. You will have plenty of terms when you multiply both of them, but the only one that matters is this one, where you see that if you take a Z1 to Z2 integral, then this is an order 1 pole, and Z3 to Z4 is also an order 1 pole. So the only piece that stays is just this double derivative here. And if you integrate this, you end up exactly to this, to the same answer as before. And it illustrates again the fact that like ANEC just acts as derivative in 2D. Now there is another way to do this, which is using conformal blocks. So the 4-point function in 2D, sorry, is just given by this infinite sum over a conformal block. So those are the conformal blocks, and this is the identity contribution. And so this eta is just the usual cross ratio in 2D. But you see that if you do this integral as before, so Z1 goes to Z2 and Z3 to Z4, then this piece just drops out immediately because you don't have the right pole structure. And then here, you can just do it explicitly and expand this hypergeometric function for small etas. And you see that the only term that matters in this sum is the p equals 0 term. So if you take the p equals 0 term and you integrate it as before, you do the 2 integrals, then you end up in the same result as before, and all the rest just drops out from the integral. So this is striking because you need an infinite number of blocks to be able to reproduce the full, just this 4-point function of local operators. But if you, instead of considering T and T here, you consider ANECs, then you just need one of the blocks, and this block is just the one where the stress energy tensor itself propagates. So what can we learn from 2D is that if you take a large C theory, then T, like these double trace operators, are vanishing when you take the integrals. So those would be the operators that would correspond to P non-zero in this sum here. And you see that they don't matter at all, and you can just consider single trace operators. And this will still be true in 4D, large gap theories. You can use the OPE to get the differential operators, and this we will do as well in 4D. And in full generality, this is not true that the ANEC is a differential operator, but if you take large and large gap, then it becomes true again. So we will see this in more details afterwards. Sorry. So now we want to see how to build these ANEC operators as a differential operator in 4D. And first, I want to review a bit of non-nullness in abounds. So the story there was to consider the integrated energy flux per unit angle on a large sphere. So you consider some perturbation in the center of Minkowski, and you are wondering if you had calorimeters that you could put in at an infinite distance far away from the perturbation, what energy would they measure? And so those calorimeters are in this case given by these energy operators that are just so energy density, and the NE tells you in which direction you put your ANECs I mean, you send your probe, and you can show, and they showed that this was related by a conformal transformation to these operators. That is exactly the ANEC operator. That you just need to rescale for by R squared if you want something finite. And then they imposed the fact that the ANEC was positive in any state, which was not proven back then, but they assumed that it was true. And they managed to get some bounds on A over C that follow from decomposing the scalar, the vector, and the tensor part of this equation, of this inequality, sorry, and to combine parameter space such that this is always true, and this gives you this region of bounds here. So in our case, what we want to do is very similar. We also want to send our ANECs to spatial infinity. So we have to choose a vector n, which is the vector that points in the direction where we send our ANECs to infinity, and then we integrate over a null line over there. And in this case, also we will call our operators energy operators. So these energy operators are just rescaled ANEC that we send to the spatial infinity of Minkowski. Now, if you compute the properly normalized 3-point function of this energy operators, then you can see that what they are is actually some transfer matrices between these epsilon vectors or tensors. So those epsilons comes from here. Those curly O are any spin S operator, but that you contract with the epsilon tensor, that is the polarization. So if you have a scalar, you have no epsilons, but if you take a current, then you will have a one vector and so on. And so this is what this abbreviation means. So this E star E is just fully contracted product, and this one you just contract appropriately the thing. And this matrix depend on the metric, on the direction where you send your ANEC to infinity, and on the 3-point function coefficients in the game. But so with this, you see that you can see the ANEC operators as some transfer matrix M that allows you to go from one polarization to another polarization state. So if you take the scalar case, you see that you have no polarization and M become 1. And if M become 1, then this whole contribution here cancel with those two. And you end up with Q0 over 4 pi, which is exactly the energy density per unit angle on a two-sphere. So you're good to go. And for U1 current and stress tensors, you end up with those two results. So you see, those are, because you're considering current, the polarization vector have only one index, and this matrix brings you from here to here. And the stress tensor case is slightly more complicated, but it's just in spirit the same. And those A2, T2, and T4 are just some linear combination of OPE and 2-point function coefficients that are unknown. And so these results are already strayed into the Hoffman-Mallasena paper. So there's nothing new in here. But so we just saw that you can obtain those transfer matrices from the 3-point function, and you don't need to go to higher point functions. So the question is, why do we want to compute the differential operators that I talked about before? I will show that those operators have an infinite radius of convergence, and so we can compute higher point correlation functions with that. And when we are able to recast it as a differential operator, then if you want to compute the product of multiple ANECs, then this becomes just a product of the differential operator. So in other words, if you want to compute this k-point correlation function of energy operators, then if you're able to get this D and to resum it everywhere, then this is just given by some energy density to the k, and then you just multiply the matrices one after the other. Okay? Now, let's try to get this differential operator. So let's start with the 3-point function. And I told you before in 2D that we want to do the OPE between t and o, and then integrate it to get epsilon o. And if you consider a 3-point function, then it's clear that the only thing that you care about on the right-hand side of the OPE is o itself, because you know that the 2-point function is not vanishing only for o, but if you have o prime, then it vanishes. So if you develop the OPE in terms of o prime, I mean, all the terms proportional to o prime will just vanish in this 2-point function. And so you only care really about the diagonal part of the OPE between t and o. Okay, and this is an exact statement at the level of the 3-point function, because even if the OPE is way more complicated than that, the only thing that you care is really the O piece. So we have a set of rules on how to build these differential operators. So here is the OPE between epsilon and this O that has been tensored with a polarization vector. So this is a scalar because this has no indices, no Lorentz indices anymore, and this has no Lorentz indices anymore as well. So you need to contract every indices, and you can build it only from those ingredients. So you have a derivative, a metric, the operator itself, the polarization vector that you will tensor, that we will multiply with O. x12, that is just the distance between the insertion of t and the insertion of o, and then you have two unit vector that points either in the plus or in the minus direction. So those chi plus and chi minus are just unit vectors that point in the right direction, and we introduce them just to be able to write everything covariantly. It has to be linear in the operator and in the polarization vector, and you don't want like higher order terms. You want to contract the position vector x12 only with psi minus. And this comes from the fact that when you do an ANEC, you integrate over x minus. So you don't want to have x minus anymore. But x minus downstairs is a x plus upstairs. So that's why it's a bit misleading. But this chi minus becomes a chi plus upstairs because you're in null coordinates. It has to have weight 3 because the ANEC, the T stress tensor has weight 4, and when you take a derivative, it has weight 3. When you integrate, sorry. It must carry a minus index, the one that stays from the dx, the integral. So you have a x minus upstairs and a t minus minus downstairs. So you have to have a SO1, minus index downstairs remaining. And if this operator is conserved, then you cannot have a contraction between the derivative and the operator itself because it vanishes. And if it's traceless, the same is true for a contraction between the metric and the operator itself. So this is just a list of all the things that our differential operator has to fulfill. And in principle, you can build any case out of this just by just summing every possible term. And we can do this in the scalar example that is just the simplest. So the only thing you can write under those rules is this operator here. So you have some sum over q, r, s, and t that are some integers. And then you can have a contraction of x12 with chi minus to some power. And then you should really think about this, for example, as a d plus, so just a derivative in the plus direction. And this is a d minus, and you can also write a box. And so now you have a set of equations that has to be true. This one comes from the weight. So if you count weight of all these building blocks, they have to add and subtract like this and give you a 3. And these equations come from the minus and plus signs. So you just need to count minus and plus indices, sorry. You just need to count how many minus and pluses you have at the right place. And the only thing you can write in the scalar case is this guy over here. So this is not particularly limiting, but you see that you have only 3 terms, so A, B, and C, that have a D minus derivatives, and then the rest is an infinite sum in D plus derivatives. So you see that even in 40, you have a finite number of minus derivatives. always, and this is true also for the current and the stress energy tensor case. And so I will show another form of this operator later that is more illuminating, but in principle, you can just build any case you want out of those building blocks. Okay. Now, if you take the scalar operators in 4D, you also exactly know is 3-point function, just given by this tensor structure, T mu nu. It's also written in this old paper by Osborne and Petku. So T mu nu is exactly known and is written in terms of the capital X, and the capital X is just some difference between the insertion where you put your operators. And for what we want to do, it's going to be more practical to define S to be x12. So S is always going to be the vector, the distance between the T and the operators we want to fuse when doing the OPE. So in this case, it's going to be x12, and V is always going to be the distance between the two remaining scalar operators, or the one that we don't touch. And so you can just write this explicitly, and you can do the integral. So again, it's you have to be slightly careful about I epsilon prescription to take things in the right order. But if you do it, you end up with this finite answer here, which we wrote in terms of just S and V. And so the whole game now is we want to show that the OPE expansion resums into this answer, because if what we learn from 2D is true, and you can really compute that sort of differential operators using the OPE, then if you add the infinite number of terms from the OPE, it has to resum to something, to exactly this answer. So the OPE in 4D between T and O, where you care only about terms that goes like O on the right-hand side, has this generic form here. Those tensors are the most general tensors you can build out of this S, that is this distance between x1 and x2, and some metric that fulfills the symmetry of the problem. So here it has to be symmetric, and here it has to be symmetric, and also symmetric in this alpha beta indices. And so if you want to get those tensors, what you do is you write the most generic ansatz, and then you put this ansatz in the 3-point function, and you compare it with the 2-point function. And so you do a small S expansion, and you manage to get order by order in S. So the 0th order will give you A mu nu, and the 1st order will give you this B, and so on. And you can just trace them back to any arbitrary order. But what you see is that if you do this, and you get this guy explicitly, and then you do the integral, so here you take the minus component here, and you do the x minus integral, then this guy drops out, and starting at C and all the remaining terms, they do matter, and they give you a contribution. And you see that what happens is exactly as if you would write the full 3-point function in this form. So here B1 is this S plus over V plus, and B2 is this contribution here. And so what happens is that if you take this and you expand for small b1 and small b2, and you do a Taylor expansion in 2 parameters at the same time, then this exactly gives you the terms that appears in the OPE, order by order in the integral. So it looks like you've managed to do what you were trying to do, that is show that this OPE reproduces the full answer for the 3-point function. So this operator that I showed you before can be written in a bit clearer way, like this. So here we took a slightly different basis, where we use d plus, d minus, and box squared only, box perp only. So this is just a box in the 2 transverse directions. And you see that each time you have a d plus, d minus, this has no indices, because d plus, d minus is like d minus, or d plus, d plus. So each time you have a d plus, d minus, you can replace it by a box that also has no indices. And you can just write the differential operator like this. And then you plug this into the 3-point function, and you compare order by order, and you manage to get this AK and BK and CK coefficients analytically. So you've managed to get a series in terms of k of the differential operator, and you can explicitly resum it. So this is what is nice: is that the OPE has a finite radius of convergence that is given by this delta 2 equal 1 coming from here. But the differential operator can be resummed and can be resummed with infinite radius of convergence. So then you can just use it everywhere. But now this is the ANEC, and what we want is these energy operators. So remember, we need to send it to spatial infinity and to transform it to an energy operator. And this corresponds in this SV coordinates to sending it to S plus goes to infinity. And if you do this, then the exact 3-point function dramatically simplifies and becomes just this contribution here. But the operator also dramatically simplifies and just has these 3 terms here. So yeah, this is really easy to compute. And if you consider the Fourier transform of the 2-point function, so you take this is the 2-point function of 2 scalar operators, and you Fourier transform it with a 0 spatial momentum eigenstates, and you act with this d, so the simplified d in the appropriate limit, then this just gives you q0 over 4 pi r squared f. And this r squared is the one that you introduce in the definition of these energy operators compared to ANEC operators. So when you go to the energy operator itself, you get rid of this r squared just to get q0 4 pi. And so if you want to compute the energy 1-point function, energy density 1-point function, sorry, you indeed arrive to q0 over 4 pi. So this is the answer from Hofmann-Maldacena. And this is also what you would expect for a scalar case, because you would expect the energy density to be distributed evenly on the 2 sphere at infinity. Okay. So this is all good, but this was for the 3-point function. And now I told you in the beginning, we are interested into computing higher point functions. And higher point functions are more tricky because in this case, you can every operator can propagate into the channel. And so this is why we will focus on large N theories. I will tell you how this buys us a way out. And I will also show you that for holographic CFTs, so large N, large gap, what I just computed is enough to compute any higher order point function of ANEC operators. So let's review a bit of large N, large gap factorization. So what we call light operators in this business is operators that have a fixed conformal dimension as N goes to infinity. And so this excludes states that are dual to black holes, but yeah, so there are light operators and heavy operators. Those are the light ones. And then you can also split them in 2 classes. One is single trace operators that are just corresponding to bulk fields. And the other ones are multi-trace operators that are corresponding to multi-particle states in the bulk. And let's review how factorization, how those correlation functions scale with N. And for simplicity, we take OO to scale like 1. If you take this to scale like 1, then OOO has to scale like 1 over N. And the connected piece of the 4-point function scale like 1 over N to the 2. But if you take, say, the multi-trace operators created from OO and you compute their point functions, then you can just recontract like this, and it just multiplies 2 order 1 contribution. So this case, like order 1, and the same is true for any of this higher point correlation function of multi-trace operators. And but you know that if you have 2 single trace operators, O1 and O2, then at large N you can create a family of double trace operators that are given by this sort of operators here. And the conformal dimension is just the conformal dimension of the two operators you consider, plus 2n coming from this double derivative and L coming from those derivatives. But this is only a leading order in N result, and this will be modified in a 1 over N expansion. But if you look at the 4-point function of 4 O's, where O are single trace operators, then this gives you a piece at leading order 1 over n. This gives you a piece that goes like this. So this is just a GF generalized free field results that applies. And so this one is coming from the identity. So you have a O1, OX1, OX2 fusing into the identity and coming back to OX3, OX4. And this one, so here you have the two permutation of this result. So where you permute where you insert your operators. And we call this symbolically double trace 0. So the 0 is here to tell you that they are at the 0th order in 1 over n expansion. And now we want to look at what happens at 1 over n to the 2. So crossing symmetry requires the anomalous dimension. I mean the conformal dimension of your operators to be modified by a 1 over n squared anomalous dimension here. But you also have the 3-point function coefficients that are modified with a 1 over n squared piece here. And the question is, how do those two contributions of 1 over n squared change our result in the 4-point function? So you have the connected piece of these 4-point functions. So this part here goes like 1 over n squared, and this goes by single trace operators. So we just call this contribution single trace here. And you have the anomalous dimension and the modification of the OPE coefficient. So those two things are also responsible for some 1 over n squared term. So this is what we call double trace to the 1. So schematically, your 4-point function of 4 single trace operators looks like this, up to 1 over n to the 4 modification. And now we want to see how those terms matters or don't matter when we take ANEC into this correlation function here. So for the stress energy tensor, the scaling is slightly different because the 2-point function goes like CT and CT goes like n squared. The 3-point function also goes like CT, so it also goes like n squared. And the normal ordered product, so those two double trace operators 2-point function, when you do the weak contraction, goes like n to the 4. So in the end, you have a scaling that goes like n to the 4 times the identity plus the double trace, so those guys here, plus those two contribution here, and some modification of the double trace here. But you see that what matters is that the connected piece is still subleading compared to the disconnected piece in this case. So we want to look at 4-point function where 2 operators are the ANECs and 2 operators are just scalar operators. And so in the first place, what we need to consider is this infinite sum over all the quasi-primers in the theory. And so these guys are both single and double trace operators, and also they corrected data. So corrected the anomalous dimension and corrected the 3-point function coefficients. And yeah, we want to see what happens with the double trace operators. So if you consider the OPE of T minus minus with O, then there is a term that goes like the normal order product of T minus minus O. And now you want to see at leading order how this 3-point function behaves. So if you take T minus minus O and this operator in a 3-point function, then at leading order, this is just a weak contraction of this T minus minus with this T minus minus, sorry. And this O is this O. So this is the leading order result. And if you integrate both sides, so you integrate on this side because you want to get one of these as the ANEC, and you integrate on this side, then you see that this integral just vanishes because it doesn't have the right pole structure to be non-vanishing. And this is just vanishing. So you see that the 0th order double trace operators do not contribute and they vanish, as well as the identity, because the same argument with the it's a slightly different integral, but the same argument goes through. And so you see that in this 4-point function, you already get rid of this identity piece and of this double trace at leading order piece. And you're left with this at 1 over n squared in the 1 over n extension. But now you want to see how those guys matter. So those double trace operators, you want to see if they matter at 1 over n squared. And so I told you there is 2 ways that they got modified. One is the OPE coefficient, but the OPE coefficient will just put a prefactor in front of this integral here. And the problem is that the integral itself is vanishing, and so putting a number here will never help you. So this will never help you, and this will vanish anyway. And the anomalous dimension is slightly more tricky, because if you do the anomalous, if you take the anomalous dimension into account in this integral, then this will not vanish anymore, but this will be proportional to 1 over n squared times the anomalous dimension. But you see that you need to integrate twice, because what you're interested in is a 4-point function with 2 annex, so you need to integrate here and you need to integrate here. So in the end, the thing you have is 1 over n to the 4 times the anomalous dimension squared. And so you see that this term does not exist in the end, and the first term where you have a modification due to a double trace operator is in this 1 over n to the 4. And you end up having the fact that the 4-point function of 4 operators is just given by 1 over n squared times the single trace. And all other contributions do not matter. From the gravity perspective, that's what happens. So these ANEC operators are just shock waves, and you want to propagate, for example, gravitons. So at leading order, you don't have particle creations. So you have a particle that you have a graviton that it hits a shock wave, and it just gets displaced, and it continues its way through. But if you wanna have particle creation, you need to put loop effects, so something like this. And this goes like 1 over n squared, this vertex here, and this vertex here also goes like 1 over n squared. So in the end, this process is a 1 over n to the 4, and this is exactly this double trace process that will be eaten in here. So what we learned is that the 4-point function that we want to consider is this one, but the sum now restricts on single trace operators. And you don't need to include every double trace operators in there. So this is a huge gain already. But there is also something peculiar about this 4-point function, is that sometimes there is one element in this sum that will be O itself. So at some point, you will propagate the same operator here and here. And when this happens, then this is exactly what we computed in the first half of the talk. So when this happens, you can just compute this 3-point function using the differential operator we computed in the first part of the talk. And this is, so if you want to compute the 4-point function, O epsilon 1, epsilon 2, O, of the O block, so the block where here it's O that propagates, then it's just given by these 2 differential operators acting on OO. But now this is not true always, and this is where we need large gap. If you focus on theory that have large gap to single trace operators, so what we mean by large gap is that the dimension of the lowest of the single trace operators that we spin greater than 2, the first one is big. Then those operators are heavy and they don't contribute. So when you do an OPE of T and O, you have only O appearing on the right hand side because the other one don't contribute in there. And so you see that if you take a CFT with large and large gap, then the epsilon O OPE only has O on the right hand side. And so you can compute this n-point function or k-point function of energy operators for all operators as just k times the product of this energy density piece times the matrix multiplication. So now we see that with large gap and large n, what we did in the first part of the talk was sufficient to be able to compute any k-point function of ANEC operators. So now with all of this, how do we show that A has to be equal to C? Well, one of the first thing is considering the commutator of those 2 ANEC operators. And if, so you have an ANEC, you write it in terms of the differential operators, and then you manage to get a transfer matrix out of this. So if those 2 operators commute, then the matrix have to commute. And so the way you want to use this constraint is directly through the matrices. So as I told you in the introduction, if they're on the same null sheet, then they're always space-like separated, and they have to commute. And the only tricky part is the point at infinity, because many different conformal transformation map to the same point at infinity. So you might be worried that at some point, even if they're space-like separated along the whole trajectory, they might touch again at infinity. But it was shown by Kologlu, Kravchuk, Simons-Duffin, and Ziboidov recently that even there they do commute, and this relies on some rigid trajectory analysis. So you can just take this for granted and see how it buys you something. So if you take the U1 current state and you just compute the commutator of those two matrices that I showed you before, what it gives you is this prefactor that is exactly A2, what we called A2 before, times this scalar product of where you put the ANEC operators and some anti-symmetrized tensor in the also depending on where you put those ANECs. But if you want this to vanish for any polarization, then what we call 8e tilde minus e has to be 0. And this is a statement about A2 and the fact that A2 has to be 0. And this, as a natural interpretation in the bulk, as a minimal coupling between the bulk gauge field and the graviton. So it will give you an effective action that looks like this. But now you can do the same with stress tensor states. And so the matrices are way more ugly. But schematically, if you compute M1, M2 anti-commutator, what you get is a T2 squared piece that multiplies some tensor structure, a T4 piece that multiplies another tensor structure, and a T2, T4 piece that multiplies a third tensor structure. And then you need to anti-symmetrize this when exchanging the two positions where you stand your two energy operators. But if you also want this to vanish for arbitrary polarization, then you better have T2 and T4 being 0, and this directly implies A equals C, because those T2 and T4 are some linear combination of A and C and other OPE data, but this directly implies A equals C. So this is the first way how we show that A has to be equal to C using this all differential operator machinery. But you can also do something slightly different. So this is the case. Here is the case for the UN current. But so if those ANEC operators are commuting and positive, then you expect their product to be also positive. So you would expect a k-point function of those energy operators to be bigger than 0. And you want to find an object that does not see the commuting properties of the ANEC operators. And one natural candidate is this object here. So you sum over every permutation of all the ANEC. And you construct this operator. And then what you do is, if A2, so this A2, if A2 becomes negative, then this expectation value becomes negative, and this is not allowed. So what you do is that you take a k, so here on the right axis you have a k, and you sum every permutation of those matrices, and you solve, then you have a big matrix that depends only on A2 and some numbers, and you solve for the eigenvalues, and you take the smallest positive eigenvalue that you can find. And you see that, so this 3 to minus 3/2, sorry, is the Hoffmann-Maldacena bound for the case of currents. So this is what a 3-point function buys you. This is because Hoffmann-Maldacena did only 3-point function analysis. This is what you get. And then if you pump up k and you go to bigger cases, then you see that this bound shrinks effectively. And you can do some analytics, and you see that this will asymptote to 0 in the end. So it's a bit computationally heavy, but you can pump up the numbers, and you will see the bound shrink here as k goes to bigger values. So I want to conclude and tell you what can also be done with this. So we studied in this paper the correlation function of ANEC operators in states that are created by local operators. And by developing the OPE between the ANEC and the local operators, we were able to recast this action as a differential operators and to know how to deal with it to compute higher point functions. And we managed to show that if you use the commutator of 2 ANEC and demand that it vanishes, then this plus large gap and large n brings you A as to be equal to C, so a weakly coupled Einstein-gravity in the bulk. And some other things that you can try to do with this kind of method is first relaxing the assumption of the infinite gap. So here we really took infinite gap to say that every other single trace operators would not matter in this business. But you can try to take a big delta gap but finite and see how A equals C gets modified. So this will be some series in 1 over delta gap that you might be able to get. Another thing you can do is analyze the arbitrary high point function of the ANEC operators. So you put all of them, say, parallel, sorry, and you try to see if there is some universal structure in there. So it looks like there is something that is universal about these correlators of ANECs. And also, you can try to learn about 6D CFTs. So in 6D CFTs, the anomaly coefficients are way more mysterious than in 4D. And it would be nice to be able to say something about A, C1, C2, and C3 in 6Ds, because it's not even clear where those guys are hidden in the 3-point function. So yeah, that was it.
Thank you very much. So, any questions? Nine?
Sorry?
The audience has any questions? So maybe let me ask what this ANEC is actually coming from. Is it information habits or because you're using?
Can you repeat the question? It's the sound is a bit hard.
So I'm wondering where the ANEC condition is coming from.
Oh, so you have 2 different proofs of this. So this is flat space proofs, but so you mean the fact that the ANEC is positive in any state?
Yes.
So there is a proof by Tom Faulkner and friends that is relying on quantum information that I'm not exactly sure how it works, and you have a proof of Tom Hartman and friends that is more CFT driven, but yeah, it's just yeah. So this has been proven to be true in any flat space QFT. It's not even a CFT result; it's a QFT result. So you don't even need CFT.
Okay. Well, then, no further questions. So let's continue again.